Hi everyone, my name is Mary Grace Carr, and this is my Physics 1 Lab 5 Choose Your Own Adventure presentation, where we will be analyzing the motion and forces acting upon a falling slinky. Before we get started today, I just wanted to give a quick synopsis of the presentation. So first we will be discussing the purpose of this lab, as well as overviewing the principles utilized in analyzing the motion of this falling slinky. We will take a look at the impact of Newton's second law, as well as the certain forces acting on the system. We will then analyze the motion of the observed data, which comes from a video on YouTube of a slinky being dropped from rest. We will then use the tracker software to track the object's position as it is released. After that, we will analyze our predicted data of the system, which will be done through our computational model made by GlowScript code. Lastly, we will analyze our results and explain why the motion occurred as it did, relating back to our physics concepts. So first, the goal of this lab. Our goal of our lab is to model the motion of a falling slinky dropped from static equilibrium and determine if the bottom remains motionless or not. So we will be comparing the observed data, which comes from the YouTube video, to our predicted data, which comes from our computational model. And in doing this, we'll be using Newton's second law to estimate the slinky's position and forces acting on the system. So we need to go over the principles that we will be using in this lab. So for this lab, the momentum principle, which is F naught is equal to the change of P over the change of T, is used to derive the velocity and the position update formulas shown here. These formulas will help us to determine the velocity and position of the slinky as a function of time as it is dropped. In addition to these principles, there are also three main forces shown here on the screen that act on the spring system, the slinky system, which include the force of gravity, the force from drag, and the force from tension. Before the top and bottom of the slinky meet, there is only the force from gravity acting on the top of the slinky, while the bottom has both gravitational and tension forces acting on it. The tension force acts in the opposite direction of the gravitational force. Once the top of the slinky meets with the bottom, the forces acting on the system change to gravitational and drag forces. In addition to this, if you consider the following equations shown on the screen, we can observe that when velocity is constant, F net is equal to 0, which means that the net force is constant as well. When velocity is not constant, F net is not equal to 0, which means the net force is non-constant. We will see this come into play in our lab. Now that we have discussed our principles utilized in our lab, we can now gather data from our observed data in Tracker. So we can see here that the origin is centered at the man's hand, where the slinky is initially at rest and then it is released. I set the weight of the slinky to be 0.173 kilograms and estimate the length of the stretched slinky to be 1.22 meters, as this is what I found online. So I'm just going to play the clip real quick, and we can see where our data is being tracked here on the right and the slinky being dropped from rest, and then the bottom and top eventually meeting each other. From this data, I found that the initial position vector to be 0.003, negative 1.218, 0, and the initial velocity to be 0 as it is released from rest. So now that we've gathered our observed data, we can now look at our GlowScript code. So here is the first portion of code that I made, which pertains to the system's initial conditions, which I described in the earlier clips. You can see that right here. So for the first while loop, I set t to be less than 5.55, as this was the time in the tracker video while the slinky remained motionless. Next, I identified the forces acting on the system at that point in time, which were just gravitational force and tension force. I then was able to apply the momentum principle and determine the changes in position and velocity through the position and velocity update formulas, which you can see here on the screen. And then here's our next while loop. So this is when the top and the bottom of the slinky met, and I have the time parameters here. And basically the same thing, calculating the net forces based on which forces are acting on the system, and then applying the momentum principle. So now that we have ran our observed data and our predicted data, we can now compare the two. So here I am in Excel with all my data on the left-hand side and our graph on the right-hand side. And we can see that the predicted motion of a falling slinky by GlowScript is very similar to my observed motion of a falling slinky through Tracker. So from our results, we can see that the model of the bottom of the slinky stays stationary, just like in the observed clip. And while the predicted and observed motions of a falling slinky are very similar, there are some slight deviations, as you can see right here in the graph. So now that we've analyzed all of our data, we can now talk about why does the Slinky system act the way it does. So as you can see, the bottom of the Slinky remains motionless. And when this happens, the net force remains constant until the top and bottom of the Slinky meet. And the bottom of the Slinky began at rest, so it remained at rest until the net force was no longer zero. And while the bottom is stationary, the force of gravity and the force of tension have an equal magnitude, so the net force acting on the system is zero. But when the bottom starts to move, both the force of drag and gravity are acting on the system, so there's no more tension force. So this is why the system behaves as it does when it is dropped.